All right, we're back. We're on page 9 of note 17. We're doing polar areas, and we're doing something weird. We're taking regions that really are best not described in polar, and we're going to find the area of those using polar area, because then we'll really know we got it right. The issue you run into is once you start doing true polar regions, you lose like your sense of whether or not the answer is right or wrong. But here, this is a triangle, right? So there's a triangle that has a base of 4 and a height of 2. So like I know the area should be 4 when I'm done. Let's see if we actually get that. So it's the region that's enclosed by y equals 1/2 x equals 4, and the x-axis. None of that is written in polar. We need to describe the region in polar coordinates. So let's take a look at the region a little more closely. So I'm definitely thinking I'm going to start here, right? So this is theta equals 0. And then we rotate through the region until we get here. And as we rotate through, we shoot out laser beams, and our laser beams are always hitting this. But let's deal with where we stop, right? We stop rotating, we stop being in the region when we get to this line. So we need to describe this line in polar coordinates. Let's also, let's do it. So this ordered pair is 4, 2. And 4, 2, so I mean, if this is theta, then the tangent of theta is 2/4. So this is theta equals the inverse tangent of 1/2. Weird, but that's what it is. So now I'm rotating through the region, right? So like picture this, just rotating, 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 rotating. We're shooting laser beams out as we do it. We're always standing at the origin. We shoot a laser beam out. It hits there. It hits there. So when it leaves the region, it's always on this line. This is x equals 4, but x equals 4 is not written in polar. So it's x equals 4. That's r cosine equals 4. So r equals 4 over cosine, or 4 secant theta. So what we're actually integrating is 4 secant theta. That's our boundary. That's r. So we're going to use, in polar, we have r equals 4 secant theta. And then our bounds are kind of weird. We're going to go 0 to the inverse tangent of 1/2. I'm definitely going to use a calculator on this. I think. Maybe not. I can, the integral of c, we can maybe do this by hand. Maybe. Maybe. I think we can. All right, so we're going to do 1/2 the integral from 0 to the inverse tangent of 1/2 of r squared. So 4 secant theta squared d theta. All right, 16/2 is 8. The integral from 0 to tan inverse. That upper bound is like scary, but maybe not as scary as it initially looks. Secant squared d theta. All right, the derivative of tangent is secant squared. So this is 8 tangent of theta from 0 to tan inverse of 1/2. This is not that bad. So this will be 8 the tangent of the inverse tangent of 1/2. But we know what that is. The tangent of the inverse tangent of 1/2 is just 1/2, right? It's like f of f inverse is just x. And then minus the inverse, the tangent of 0 is 0. So this is 8 times 1/2. This is 4. We set it up and we did it correctly. We got 4, which is what we were expecting. I mean, it's just triangle. So this is a ridiculous way to find the area of a triangle, but great practice. And that's why we're doing it. All right. So polar regions, like the subtle differences create huge differences, right? So here you start out here and you rotate, but you're not hitting the region. You don't hit the region until you get to this line. So this is the line we're going to start at. So I need to know what that is. So we're starting when we get here. Okay. You know, it's like you should never start unless you're going to get it right. Okay, so what is this? This ordered pair is 8, 4, which means that this is, it's actually the inverse tangent of 1/2 again. I don't know if I meant to do that or not, but I did it. So now think about how a polar region works. So polar region, you are always rotate. You always want to be rotating counterclockwise, basically. So we hit the region here, and we keep rotating, keep rotating. What value of theta do we stop? We stop there. So that's the end of our region, and that is theta equals pi over 2. So we're going to go from inverse tangent of 1/2 to pi over 2. Now, as we pass through the region, right, we're rotating, we shoot a laser out, and we're always hitting the outer edge of the region when we get to this line. That's y equals 4, but that is not polar. So y equals 4, which means that r sine equals 4. So r equals 4 over sine, or 4 cosecant theta. So our region is going to be the polar curve is r equals 4 cosecant theta. And then our bounds are gross. It's tan inverse of 1/2 to pi over 2. And now we just set it up and see if we can do it. So, I mean, probably 1/2 the integral from the inverse tangent of 1/2. We should just name that like k or something, but I didn't. To pi over 2 of r squared, and then d theta. Okay, so that's 16 divided by 2 is 8, and then the integral and inverse of 1/2 to pi over 2. Cosecant squared of theta. The derivative of cotangent is negative cosecant squared, so this will be negative 8 cotangent of theta from the inverse tangent of 1/2. So I'm going to have to do the cotangent of the inverse tangent, which I might need to think about, but also is just going to be 2. So, you know, it depends on how much you want to think. So negative 8. Cotangent of pi over 2 is 0. And then minus the cotangent of the tangent inverse of 1/2. Okay, so that's negative 8, 0, minus 2, which is going to be 16. So 16 right. This is a triangle that has a base of 8 and a height of 4. So that would be 32 divided by 2 is 16. So we got it. Nice. All right, let's do one more. This one requires less setup because it's just nice circles centered at the origin. Those are the best. But think about it. We got like, let's say that R1 is 5 and R2 is 4, right? A circle of radius 5, a circle of radius 4. They both are going to take 0 to 2 pi. So there's two ways of thinking about this, and you should think about it both ways. One of them is you're just going to do like big minus small, right? The big area is going to be 1/2 the integral from 0 to 2 pi of 5 squared d theta minus the small is going to be, so minus 1/2 0 to 2 pi of 4 squared d theta. And you can totally like do both of those separately, totally fine. But they have the same bounds. So this we could combine into 1/2 the integral from 0 to 2 pi of the big curve squared minus the little curve squared d theta. So it's square and then subtract. Square and then subtract. Where have you heard that before? Volume of revolution, right? Big volume minus little volume. Square it, then subtract. You don't like subtracting then square. That's crazy talk. So this would be 1/2 the integral from 0 to 2 pi of 25 minus 16 is 9 d theta, which gives you 9/2 theta, 0 to 2 pi, which again is giving us 9 pi, which is like the answer of the day, it turns out. All right, so this one's like real polar. Like, again, you wouldn't really use polar on this because why are you doing that? It's obviously, it's 25 pi minus 16 pi is 9 pi and you're done, like geometry. But polar coordinates will also get it for us, and we're getting better at setting up and evaluating the polar areas. That's why we're doing this. All right, I will be back in the next video to work on the next page with you. So I will see you there.